which means that we're going to have to re-engineer our search engine to actually support this idea of searching for a sequence of tokens inside of a larger tree. So what do we want our language to actually look like? So in terms of syntax, we want to support things that existing languages already supported. So we want to support any potential token that you might have in your source language that you're searching over. But we also want to support these two key ideas of, that we're going to call a subtree wildcard and a siblings wildcard. And this is kind of inspired on existing work on kind of like expression placeholders or like any number of items in a list placeholder. And what we want this this search queries to actually work, the way we want them to actually work is I'm going to demonstrate with an example. So if we have a query that looks like this, it's inspired from our first example. We actually wanted to match things like this, where we have a tree that has exactly 2 arguments, right? But we don't want it to match anything that doesn't have any arguments or that has only 1 argument, because of this idea that the comma is actually encoding this fact that we're expecting it to have more than 1 argument. And similarly, we wanted to be able to encode this wildcard expression. We also wanted to encode arbitrary trees, right? So in this case, we have the ternary operator as a first argument, and we actually want to be able to support that kind of use case. Yes. So roughly speaking, we want concrete tokens to match to concrete tokens in our tree. But more complicated, we want this idea that the subtree wildcard is actually going to match with entire subtrees, right? And so this is going to be the thing that actually encompasses this idea that it's going to match an entire expression or an entire statement, which is what existing tools actually support. Furthermore, we want sibling wildcards to actually match this idea of a set of contiguous subtrees, right? Like the elements inside of a list. This is the last time I'm going to mention sibling wildcards, but you can read the paper for more details on how these are supported. Yeah. So what does the actual matching process look like? So here's the algorithm that we came up to actually implement the semantics. And I'm going to briefly walk you through it with an example. So here on the left, I'm going to have the trace of function calls to this match because it's a recursive function. And I'm going to show you, where we are in a tree based on this diagram in the bottom, where I'm going to use a number to represent where the cursor is in the tree. So the very first thing that we see is that when we're matching a concrete token, in this case the authenticate token, is just going to go to this bottom part of the code. And what we're going to do is do that idea of matching concrete token to concrete tokens. And so we're going to match this authenticate token, and we're going to see that it actually does match. And so we're going to move on to the rest of the tokens and the next subtree. And once again, we have a concrete token, so we're just going to perform that match directly. But now we actually have a siblings subtree wildcard. And this is where things are interesting. So the subtree wildcard has to match an entire subtree. But it can match any subtree immediately after the last token, right? So it can be any subtree in the left spine of this tree. So how do we pick? Well, for this we just actually use standard backtracking. And so we first guess that it's the largest possible match here. And so we guess that it might be the entire set of arguments. But then once we try to actually use that as a match, what comes after the list of arguments is actually going to be the closing parentheses. And so this is actually not going to work as intended. And so for this, we backtrack. And now we try the next possible subtree, which is the first child of our original subtree. And then we continue matching again for the next concrete token. In this case, we're going to actually see that comma, and we're going to actually succeed. And once we run out of tree or we run out of a sequence of tokens, we actually know that we finished matching. So I'll briefly touch on the complexity of this algorithm. We didn't really spend a lot of time optimizing this algorithm. It has some backtracking involved, so there's an exponential in there. But in practice, we actually expect most of these numbers to actually be fairly small. And the reason for this is because this is actually based on code, right? So k in this case is the length of our query. D is the depth of the tree, how nested your expressions are inside of your language. And H is the number of wildcards in your query. So based on our benchmark, the median values for this is fairly small. They're all under 20. So we don't actually expect this to be a problem, and we empirically confirm this in our evaluation. So talking about the evaluation, how do we make sure that this tool is actually doing